My hand puppet version of the talk is really very boring, so it was worth it, I hope. So I'm going to start by saying that astronomy is one of the oldest sciences. This is a picture of a stone tablet of the recording of observations of Halley's Comet over 2,000 years ago. And this is one of the advantages of astronomy, that you can go way back in the historical record and find events. But even after thousands of years, the precision didn't really get any better. Here are two much more recent records of the same comet. But if you really want to start to study the physics and understand the universe, you need something a little better than this. So where we start to really gain in astronomy is when we have very good data. This is one of the most famous examples. One of the early astronomers, Tycho Brahe, took very precise measurements of the orbits of Mars. And then he gave them to Johannes Kepler, who he was actually feuding with at the time. But these observations were so good that Kepler couldn't make a circular orbit of Mars work, even when he had already put the sun at the center of the solar system and all these things. And he was forced to derive his laws of planetary motion, and that is that the planets go around the sun in elliptical orbits and not in circular. And this is one of the earliest examples of very good data in astronomy actually forcing new physical understanding of our universe. Now, today I'm talking to you about exoplanets. In the world of astronomy, exoplanets are very new. Exoplanets are simply planets around things, stars, other than our own solar system. Now, 25 years ago, there were only 9 planets. This was before we kicked Pluto out of the club, after all. And these were all in our own solar system. And then people started to see very odd signals around both pulsars, which are very old, strange radio stars, but then in '95, two independent groups, claimed that they saw a signal around a nearby, very sun-like star, and that they had ruled out almost everything else they could think of, and that the most plausible explanation left was that there was a massive planet going around this star. And since then, we've had a real explosion. Let me see if I can make this movie work. This may be too much for the technology. A real explosion, and this is just a little time-lapse movie of the discovery of planets. It's their period around their stars versus their mass. And you can see as the years go on, the exponential growth in the number of planets. And in 2014, we've had more planets discovered in the 1 year than in all the previous years put together. And so now we can start finally asking the big physics questions, because astronomy is really just about understanding the physics of the universe. So simple things like how many stars have planets? How big are they? Where are they located around their stars? What drives the diversity? One of the things that I find incredibly interesting is we now know over 400 stars that have more than one planet. But absolutely none of those systems, and one of them has 7 planets, but none of them look even remotely like our own solar system. In our own solar system, we have small planets close in and big planets far out. We've yet to find anything that looks remotely like that. And then you can start asking even bigger questions that go beyond astronomy. Are these planets habitable? You start getting into the world of astrobiology. And then the biggest question of all, are we alone? So to do this, we need to gather the data on exoplanets, because we really need the hard data to do the physics. So I work for a group that runs something called the NASA Exoplanet Archive, which is funded by NASA, obviously. And so our mission is to try to facilitate this for professional researchers. So we have things like lists of exoplanets, we have lists of candidates, we have data on millions of stars that have been searched for planets, which may or may not have signals in them. We work very hard to curate this data by updating it weekly when new results are available. We work on both ground and space-based missions. And so we have decided to use just things from the peer-reviewed literature. There are things that are put out on the web. There are preprint servers, there are blogs, and so on. If you write a blog today and say, I found a planet, that's not going to make it in our archive. You've got to get it past at least a peer review professional journal. One of the things we've tried to focus on is bringing in larger data sets that are maybe more work than a small university group could do on its own. And one of the failings of astronomers is that when we do new surveys, we often give new names to the objects, even though we know perfectly well that all these stars, generally, have already been seen in many other surveys. So one area in which we spend a lot of work was doing what we call cross-matching. That is, identifying an object in one survey with an object in another and saying, yes, these are indeed the same star. And then because we work for NASA, one of our other primary missions is to make sure all the specifically NASA-supported things are preserved so that when the mission itself is done, the archive serves as a place, the official repository for the data. So I could spend easily an hour just talking to you about fun little facts about exoplanets, but since this is a data meeting, I'm going to tell you some of the issues and challenges that we face and how we've come up with solutions, which are similar to some of the issues that have been raised before. So our first issue is just keeping up with the peer-reviewed literature. We're a relatively small group, and as several speakers have already said today, this isn't something that OCR can magically be solved because there's a lot of context involved. So at the first level, last year there were roughly 500 papers in the professional literature using the keyword exoplanets. So we had a scientist read the abstract of every one of those and decide, yes, this really is relevant to us and we need to deal with this paper. We then have to go in, extract all the relevant data, validate it, and get it into the archive. Getting into the archive is easy. It's the extracting and the validating that's difficult. So some of the issues that we have, it's different than the insurance maps that we heard about earlier, but we do have our own issues. Another failing of astronomers is we can't agree to all use the same units and the same reference points. So I have a little table here of just within the chime system called Julian date, there are 4 systems that people use. And there's a whole other system of times that people use. So you have to figure out when someone gives a date in astronomy, you have to figure out what kind of date is this, because in the archive, we need to put that on a common reference frame so that all the data can be compared. Another problem is that people aren't necessarily thinking that this is going to go into an archive, and so very important data will just be embedded in text. And so again, there's no easy way to get that out other than very manually. So we have dedicated archive staff that this is all that they do. We are working to make this better in our field, working with some of the other astronomy data archives to try to set standards for people. We're hoping that if we actually have templates and guidelines, people will try to be a little better about getting their data in a format that makes it much easier for the long-term preservation. The second problem, and this is somewhat specific to exoplanets, because several of those questions I asked, you want to know not only where the planets are, but you want to know where the planets are not. So if you want to answer the question, how many stars have planets, I not only need to know how many planets you found, but I need to know how many stars you looked at, and ideally which stars you looked at, because then I can compare to this other study, which looked at a somewhat but not completely overlapping set. But right now in academia, it's very competitive. There's many more postdocs than there are faculty positions, and there's a lot of social pressure, I'll call it, to publish just the positive results. And so someone will say, they'll do a survey of 1,000 stars, they'll find 5 planets, and they'll publish that, and we'll get that data in the archive. But they won't publish the list of the non-detections, as we call them. And we have relatively low detection rates here, up to a few percent at best. And so there are many, many more stars that have been searched than planets that have been found. If we don't know that, we're really incomplete in our knowledge. So the long-term thing is you need to change the culture. And we're working on that, but that's hard for any one group to do. In the short term, we're trying to give essentially financial incentives. We have a little bit of grant money. We can give someone to give their graduate student. We'll help you pay your page charges. But that's very intensive as well. We have to do that one-on-one groups. But we are making a little progress that way. The third issue is about data diversity. And this is perhaps the most interesting one because it's not clear to me what the solution is. So there are many methods of discovering planets, and I'll tell you a little bit about some of them. But each of them measures a different subset of the physical properties that we're interested in, and no single method gets them all. And so here's just a sort of summary of the kinds of things we're interested in. We want to know what the central star is. We want to know what the planet is, particularly its mass and radius, because then you can do density and composition. We want to know how far it is from the central star, how long it takes to go around. Now we go through the 4 most prolific methods of planet discovery. So the first is transits. These are ranked in order of the number of planets that have been found in it. So this is very simple. You have a bright star. The planet passes in front. The planet isn't self-luminous, and so it's now blocking light. So you get a little less light from the star when the planet's in front of it. So this is very simple. Oh, it's simple to describe at least. It's actually hard to do in practice because very little light is blocked. But you also have to have the alignment of the planet's orbit with the line of sight to Earth. So this has a very low rate of success just naturally because even if you have a lot of planets, most of them won't be aligned with this line of sight. The second is maybe the most famous method because this is the most common for the first 15 years of finding planets, and that's called radial velocity or wobble. You have the gravitational influence of the planet as it goes around the star. That's actually enough that the star is actually moving, and so you can see a shift in the spectrum of the star if you observe it. And so this is not relied on the inclination angle, so is much more, has a higher rate of success. The third is the most direct and the most recent. So this is imaging. So this is very simple. These are the only real astronomical images I'm showing in this whole talk. These are actual exoplanet systems. The one difficulty about this one is that the star is so much brighter than the planets, and you're seeing the planets in reflected light, not in direct emission from them. It requires relatively sophisticated methods of blocking the light from the star. And that's why the images look a little funny in the center. Those are spots that the light from the star has been subtracted by various means. But what you're left with is just a direct picture of the exoplanets. And then finally, probably the most obscure method of these four main ones is called microlensing. This actually invokes relativity and the gravitational distortion of light. If you have a very distant star and a somewhat near one, the light from the distant star will be warped, and you'll get a momentary increase in light as the star in between passes by. If that star in between then has a planet, you get a little blip on that signal from the gravitational influence on the distant star's light. So this is very obscure, but it's actually very powerful because, as I'll show you, it probes a different kind of planet than the other methods. Okay, so now going back to this idea of the subsets of the physical properties that we're trying to find out, we can look at each of these four methods. So the transits, for which we've found many planets, are great, except you have no idea what the mass is. You can see what the size is because you can see that light is blocked, but you have no idea what the mass is. And then conversely, radial velocity, which accounts for the other big chunk here, you get a mass, although you have an ambiguity due to the sign of the inclination, but you have no idea what the radius is. So these are the two fundamental properties of any planet, and the two big methods together don't measure them. Imaging and microlensing are very similar in that it's somewhat model dependent on getting these things out. So what happens when you make a table of all these planets, as we have done, what you end up is with a somewhat sparsely populated table. So this is a real snapshot of known exoplanets that gives you a flavor of how badly astronomers name objects, but also gives you a flavor of all those blank cells or where there is no data in the literature, and in fact is unlikely ever to be data in the literature for those quantities. So we have this issue now as scientists. How are we going to actually ask and answer these big physics questions without being able to populate this data? So in some ways, there is no solution to part of the problem because it's just fundamental to the fact that these discovery methods are different, and you can't always use the same method on planets. So this is now phase space of period versus mass for planets, and the four methods roughly with their current sensitivities. And you can see there's a relatively large overlap between the transits and the radial velocity methods, but remember the transits only happen if they're edge-on orbits. And so in fact there is relatively little overlap. And then the other methods, it's great that they probe different areas, but it's bad. It means that very few planets have all these physical properties measured. And you can see that now if I plot up the real data on those same axes, and now they're color-coded by these different methods, you can see there's very little overlap between these samples. And so anyone looking to study these samples is going to really have to take that into account. And so what have we done? I mean, we can't solve the fundamental issue of taking data where it just can't be done, but we're trying to work with researchers to do the best that we can. We allow them to do subsamples. We always link to the original data and source. We provide counts for those doing statistical work. And here's just an example of a group working on what we call population synthesis. They're trying to understand the big questions of exoplanets by starting from the physics of how they form and then looking at the observed population. And then they do a comparison to the subsamples after they've applied these biases. And this is where the archive comes in. We allow them to select out the different properties in the different samples to compare to. So I just want to end with, on a somewhat upbeat note, there are some planets where we do actually know everything that we need to start asking the really interesting physics questions. So there are those planets which both transit and have had radial velocity data taken. And from that, you can get both the mass and the radius. And that's incredibly important because then you get density. And density is actually when you can start comparing to things that we understand here on Earth. So here's a little plot of some of the better known, better characterized small planets. So you can see Earth and Venus down there in the corner. And then the lines are lines of constant density. And the bottom red line would be a world made up entirely of iron. So that's basically the most dense thing that we can imagine realistically forming around another star. And you can see nothing is particularly close to that line. And then the top blue line is majority water with some other minerals. And you can see there are quite a few things up. But one of the interesting things here is particularly when you look at the position of Earth and Venus, which are planets that we hopefully understand relatively well, you can see there's a huge range. There's this world called Kepler 11F, way up there at the top there, much, much less dense than any of the small worlds in our own solar system. And so now we can start finding out, trying to ask the questions, why is that, where did that form, why is it so different than the worlds that we have here? And then from those gold standards, there's even a better set. The brightest ones that are nearest to Earth, we can actually do a method of detecting what's in their atmospheres. Now, not all of them have atmospheres, but a few of them do. And we've gotten to the point we've detected molecules in the atmospheres around planets around other stars. And this is just beginning, and is an area of very active research in astronomy, but we found some of the basic molecules, water, carbon dioxide, methane, and we're building up a library. Again, we haven't found anything that looks like any of the planets in our own solar system. And so it's opening up even more questions of why is that, why is our solar system like it is, in fact? And so this is an area where there's going to be a lot of new discoveries in the next several years. So I know I'm standing between you and lunch, so let me just sum up by saying that in the last 25 years, we've discovered over 1,700 planets around other stars. But the process of really understanding them is only just beginning because we've only just gotten to the point where we have enough data to actually start challenging physical hypotheses against this data. And so what that requires is not only preserving the data, which is really not that difficult, but actually understanding its context and the biases, which is turning out to be a much more difficult problem. And I will end on an optimistic note in that exoplanets are very big right now, and there are many, many missions, both in the planning stages and underway, that are going to expand these counts tremendously over the next 3 years. These are just 3 that I'm highlighting because they're large space missions, but once they're done, we're going to have tens of thousands of exoplanets that we know. Thank you.